Okay, I got it.
Is that okay? So,
Yes.
so first we look at this. Tangent to x, when x approaches 0, this is tangent.
You forgot to stop sharing.
Thank you, sorry. So tangent approaches 0. Then I identify the fact that this approaches 0, as x approaches 0 from the right. So then I know that this is an indeterminate case. This is one of the three powers, the most cumbersome, the longest. Also, please remember, we always say from the moment we open our eyes on algebra, we say any number raised to 0 is 1, except, and now you will see why, right? Except 0 raised to 0. So in a beginning algebra, intermediate algebra, we always write this. And we tell our students, any number raised to 0 is 1. But then we have to say, except 0 raised to 0, because this is an indeterminate case. It's the type of no clue, if you want. If you don't want to call it indeterminate case, it's the type of no clue, meaning it can be anything, simply anything. Okay. Now, I want to connect some topics here. At some point in time, a month ago or something like that, or less, we talked about a function raised to another function, prime. So let me put x so it's clear. Prime. What did we do with this? Anyone remembers? So you can say, what are you doing? What is this? Just a refresher. Not connected. You will see the connection in a minute. So how did we differentiate a function raised to another function? What did we do? What was the procedure? What did we use?
You would use the natural log.
The logarithmic differentiation.
Exactly. So let's take a look. Oh, function raised to a function. That's why I wanted to connect these two. Of course, it's not the same thing. We're not talking about the same thing. This is a limit. This is a function differentiated. But we applied the same procedure. We applied log first. That's exactly what we're going to do there. So the function we are looking at is y equals tangent to x raised to power x. Yes. And I'm not differentiating, but I have to apply the same procedure. I have to apply natural log to both sides. Great job. Thank you. Okay, so I don't have the limit right now. I'm only focusing on the function. So the function is this. We apply natural log to both sides. This becomes natural log y. This becomes x times natural log of tangent to x. Okay, now apply the limit to both sides. I applied natural log to both sides. Now apply the limit to both sides of this. So this is step number 1. I apply natural log. In step number 2, I will apply the limit to both sides. I know what you're going to say, and it's legitimate. And I'm going to tell you what you're going to say. You're going to say, and I will have to say, yes, I agree with you. What are you doing? The problem was asking us to find the limit of a function. Now you're finding the limit of the natural log of the function? What is going on here? And then I will say, you're right. Please wait till the last step. And you will understand why we need to do this. Okay. But you're right if you say that. Hold on. You're determining the limit of the natural log. You're not determining the limit from the function anymore. And I'll say, yes, you're completely correct. And we will get back to that. Okay, so now we're focusing on this. Limit as x approaches 0 from the right. I need to know where this is going. Because now, again, I have to discover what this means. Where is this going?
0.
Perfect. So now, where is this going as x approaches 0?
Also 0.
Excellent. Now, where is this going? Natural log of 0 from the right. Let me refresh your memory on the graph of natural log.
Infinity.
Careful. You're right with infinity, but it's negative. I agree. So this approaches negative infinity. Look at that. What type of indeterminate case do we have now? What is the no clue case at this point? Yes. Infinity or negative infinity is not important, but I want it to be specified. Yes. What do we do with this? So by simply applying limit to something else, I know, we change the ugly situation of 0 raised to 0 into a much nicer situation of 0 times infinity. How do we address this in general? What did we just say about this? What method do we try to apply here?
See what it tells. Oh, the manipulation.
So I need to do something to this, something legitimate, obviously. So limit as x approaches 0 from the right. I will never try to do anything with the log. This is very important. Don't touch the log. Leave the log alone where it is. But instead of this, I'm going to do this. You can say, wait a minute, wait a minute, wait a minute. How come that these two are the same? Yes, because when I divide by a fraction, I have to flip the fraction. And I cannot do anything to log. Log is carved in stone. The only piece I can manipulate, so to speak, is this. I can erase it. I can bring it to the bottom as 1 over x. When I divide this by a fraction, I have to multiply by the multiplicative inverse of the fraction. I get that. But now I'm happy, super happy. Because when x approaches 0 from the right, you remember the graph of this. Please remember these graphs. They are the milestone. See? This goes to infinity. And this we already know it's going to negative or positive. It doesn't matter. It's infinity over infinity, any sign. So, yes, we don't like it. We're not there yet. We're applying the limit to a natural log. Okay. But that allowed us to change 0 raised to 0 into a product. And the product is, I shouldn't say never, but in general, not difficult to handle with a simple change of the function. I'm not changing the function, I'm changing the presentation of the function. And look, I got what I wanted. This is all I want, either 0 over 0 or infinity over infinity. And now I will differentiate top and bottom applying L'Hopital's rule. Can anyone give us the derivative of the top?
Uh, 1 over tangent 2 times 2x. 1 over tan 2x times secant squared 2x.
Excellent. Times?
2.
That's it. Great job. Thank you. And now we know how to differentiate this. What is that?
1 over 2x.
Careful.
Negative 1 over 2x.
So we had it here. Please try to remember this. It's very useful for chapter 5. So negative 1 over x squared.
it.
Okay. So now, of course, I have this in the way. So I'm going to say next page. And that's 10. Okay. So I'm just going to put here a circle. Okay, so let's see what I have here. This can go in front. This approaches 1. I want it out of there. Done with it. And this is a minus. I'm going to put the minus in front as well. So then I have limit as x approaches 0 from the right. The top is 1 over tangent to x, and the denominator is 1 over x squared. How do I divide two fractions? I flip the denominator. So this is negative 2. Limit top is x squared over the denominator, tangent to x, and x approaches 0 from the right. Notice something very important. I had to get this done. Apply the limit to this, because if I still keep it there, I'll never get the result, because I will have to differentiate a ratio. No. It happened that this is very nice. Secant squared of 2x when x approaches 0. Remember, cosine approaches 1, secant approaches 1. This is gone. And 2 has to stay in front because this approaches 1. So now, let's see what we have. Where does the top go? Where does the bottom go? We know what our hope is. We only have two hopes. Where does the top go?
0.
Yes. Where does the bottom go?
0.
Yay! Negative 2. Limit as x approaches 0 from the right. Can anyone give us the derivative of the top?
2x.
Excellent. Can anyone give us the derivative of the bottom? You already told me, Sean told me already.
Yeah.
Secant squared of 2x times 2. I simplify. Where does the top go?
Zero.
Where does the denominator go?
1.
That's it. How much is negative 2 times 0 over 1?
0.
That's it. Okay. Wait. I'm going to copy in step 3 the beginning of step 2 and the end of step 2. So in step 3, I have limit as x approaches 0 from the right from natural log y equals 0. I copied the beginning of step 2, blah, 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 and the end of step 2. And now, do you remember a long time ago when we studied the limits, the rules, the limit rules, and I said this: limit of the square root of a function as x approaches a is the same with, anyone remembers? Under continuity, of course, only. Swap the operators and tell me what to write. Anyone?
Is that the limit of as x approaches? Oh,
I'm swapping the operators. Limit is outside, the square root inside. First, I have to apply the square root and then the limit. But I'm allowed under continuity to swap the operators and say, I'm going to apply the limit to f and then take the square root under conditions, and the square root, whatever I get, is not a negative number, etc., and the function is continuous. So what do you think I'm going to do here? I'm going to swap the operators. I'm going to put this operator outside and this operator inside. So I have natural log of the limit of y as x approaches 0 from the right is 0. And I'm going to ask you, what could this be? Natural log of what is 0? Or?
1.
Exactly. E raised to 0 has to be 1. So our limit from tangent to x raised to x as x approaches 0 from the right equals, again,
At each 0.
1.
1.
Yeah.
So this can only be 1. Only natural log of 1 is 0. And what is this? What I wanted, what I was looking for. The limit of tangent to x raised to x is 1. So we got the answer in a roundabout way, applying natural log, applying the limit to natural log, and then at the very end, swapping the operators. We are allowed to, under conditions of continuity, we are allowed to swap the operators, and then all I had to do is think. E raised to 0 is 1. Yes, it